My guest today is Richard Campbell. Richard, how are you, my friend?
It's great to be back, friend. I think the last time we did this was it in Kansas City? I think
It
it
was in
was.
Kansas City. We were in
Yeah.
person. We actually saw each other and recorded
Yeah.
something in person.
We sat in the corner of the big hall there away from everybody and just chatted for a little while. I think it was space stuff too, if I recall.
It was, yeah. And we're so we got a chance to chat and sit in a corner in London last
Right.
month, but we didn't record that.
No,
And,
it was so busy too. Like that
it was really busy. It was a great time. I was just having too
intense
much
show.
fun to stop and pull out my recording equipment. But
That's fair.
I really wanted to talk to you on camera, so thank you for making the time for this.
Oh, always happy to.
All right, let's talk about energy, because I know
Okay.
you're a fanatic about learning as much as you can about energy.
Well, this has been an ongoing thing because of the Geek Outs on .NET Rocks, right?
Yeah.
Carl convinced me to start making these shows, which I didn't think was a good idea, but I was wrong. And we for a while there we were doing them every month, but as things changed, now we only do Geek Outs a couple times a year. Typically around Christmas and New Year's, I'll do a recap on the state of energy generation on the planet and the state of space on the planet, which has gone through an astonishing set of changes.
Sure.
But the energy recap's a good one because there is, in general, a motion towards lower carbon emission energy everywhere. And we're the funny part is generally the messaging from the folks that are concerned about this is very negative, that we're in terrible trouble. Climate change is serious. We're not going to reach the goals of the Paris Accord and so forth. But we've made more progress than they care to talk about. There's an argument we're about a third of the way along.
Third of the way along to what?
To generating energy with non-carbon emitting sources.
Oh, interesting. Okay.
Like this, and it's more than just how you generate energy, but other carbon emission sources, the increase in electronic vehicles, the decrease of emissions around industry. Like there's lots of different pieces in motion.
Mm-hmm.
Like if you go all the way back to the Kyoto Accords in the 90s, the projection was a 4-degree temperature increase. So that issue is off the table. We're struggling we want to stay at 1.5, and we're not going to make it. The number's somewhere between 2, maybe 2.5. So we've
You're
already
talking
made
about
progress.
the global average temperature of the Earth?
That's right. That's right.
Yeah.
So I mean, things have come along, but the problem is if you cast straight lines on any of those curves, they always look worse than they are. And real curves are duck curves. They twist and turn a bit, and so we're accelerating up a curve. We've learned a lot about making low carbon energy these days, and got it to the reasonable price. Like the least expensive power today, if you measured in what they call LCOE, or levelized cost of energy. So that is the total cost of construction, the total cost to operate, to clean up afterwards over its lifespan per megawatt. Cheapest power out there is wind. And then the next cheapest is solar. So, I mean, they used to be extremely expensive to build and operate. And now they've gone down in price so much that they're actually cheap power. But they aren't base load power.
Base load, what do you mean?
Space load means that I can run it as much as I want at any time I want for exactly as much as I need.
Okay.
Solar makes as much power as it can collect at any given time. And in fact, one of the problems with solar is that sometimes it's making power when you don't need it.
Okay.
So in places like Australia, specifically in like the southeastern part of Australia, New South Wales, and cities like Sydney,
down there.
Lots of sun, and very popular to put solar on the roof there because they get such good returns on it, to the point where it's now starting to destabilize the grid because it's more during the middle of the day when they have a lot of sunlight, but they actually don't have that much power consumption. The power consumption is heavier in the evening. There's nowhere to put it.
And so the batteries or whatever it is storing this power doesn't have the capacity. What happens when they get overloaded like that? They just throw it away?
It'll cause fires. Yeah,
it causes fires. It can't just ignore when it gets past capacity.
No, it's a problem. And so one of the things they have now, if you're going to put solar on a roof in a place like Sydney, is that the power company can disconnect you.
I see.
Right, to try and stop those overloads. Like these are problems we never used to have. Before this movement, you had a handful of large power plants. We tended to build them as big as possible, so you didn't need very many of them. You had complete control over them. They made exactly as much electricity as you needed. And your job as a power operator was to anticipate energy demand hour to hour and ramp up and ramp down to make only as much electricity as needed. And then we introduce wind and solar, where we don't really have control over that. They tend to be small. There's lots of them. They're
Okay.
not as controllable, and we just haven't had that two-way system. Now we've made vast improvements. Most of your audience, certainly my audience, being from the internet class, like folks who know our way on internet, we're not freaked out by concepts like peer-to-peer networking. But in the power industry, that was just a bizarro land. They're strictly
Hmm.
top down. We generate power out to the places that need it, and that's all we do. This
Ah,
idea that you need to take feedback from lots of different sources and have precise control in lots of different areas, it's just not something that ever dealt with. So the real transformation that these new power generation sources have created over the past 20, 30 years has been changing the way command and control works for power generation for a given area.
interesting. So, are there circuit breakers in place that can automate this, or is this
That's
a
right.
manual process that?
Yeah, generally they're as automated as possible, but originally they weren't.
I see.
You know, the biggest problem with the biggest thing you do with electrical generation is try and do it safely. And
Okay.
so if you've got above ground power poles like I have up here on the coast, all those lines are exposed, and when trees hit them, they will cause a fire. And so
Right.
there are interrupting breakers all the way along the lines.
Hmm.
They're literally up on the poles. And so if there's ever a short, that breaker pops, de-energizes the line so that the wire does come down, it won't hurt anybody,
Hmm.
and it won't set that tree on fire, which is all these are all good features, but it also means power's out.
Right.
And so, where we are here, if there's a windstorm, power goes out all the time. It's pretty normal. But there's
Sure.
also a crew that will now go, and their main job is now to inspect the line. They know where the outage is and see if there's anything stuck on the lines. Often it's fallen off, or it was an unfortunate squirrel who connected the wrong two things together and is now cooked.
Now a late
And
swirl.
once they see the line is clear, then they'll take a big pole and reset that breaker up on the pole, and power comes back. So there's no real repairs. It's just that the safety system needs resetting.
Hmm.
But when you get into systems like rooftop solar at a large scale, or large wind farms distributed over a large amount of areas, you kind of need a certain amount of control over each one of those, and that's challenging.
Right.
So
Especially if everybody has one.
that's right.
Everybody's got panels on their roof. That's suddenly you don't have one power plant. Now you have
Lots.
millions of power plants.
Although, I mean, realistic when it comes to residential solar, that is primarily designed to be used in the home that it's on. It's actually
Okay.
really hard to send power back upstream
Okay.
once you've got it down to residential levels. When I'm distributing power in an area, I tend to do it at a higher voltage because it transmits more efficiently.
Hmm.
And then I step it down. That's what those transformers are up on the poles, is I step down to the voltage that's safe to use in a house.
Hmm.
And the solar panels that are on my rooftop are also designed to work at house levels too.
I see.
So pushing it back up to the higher voltages isn't efficient. Now, this is different from commercial solar. So if you
Okay.
you take a few acres of land that's got a good southern facing, if you're in the northern hemisphere, and set up a bunch of those panels, you actually run them at commercial voltage levels so that they can be inserted into the grid easily.
Okay.
Different from residential solar. So, and that's part of this challenge here is like the price LCOE of commercial solar, very cheap. The price of residential solar is not that cheap. Like it's pretty expensive for the amount of power that you generate.
Interesting. If it's that expensive, why are people doing it?
Well, because electricity is expensive in
Oh.
different parts of the world. And so the fact that I can take a certain amount of my power bill away, you do have a return on investment, depending on where you are, of 5 to 20 years. To the
So
point now
is
where,
that upfront cost of the hardware of installing these solar
yes.
panels, but then
And
the
these
cost
days,
per watt, I guess, is
yeah,
less than getting it from the electrical company.
even up in a place like here in British Columbia, which we're pretty far north, right? This is
Right.
beyond 49 degrees north. There's a solar company out here that will take a look at your existing power bill and will basically say, okay, we're going to no upfront costs to you. We're going to continue to charge you what your power bill is for the next 10 years. We're going to install the solar, and it's going to reduce your bill enough that we make money, even covering the costs of everything over that 10 years.
Hmm.
So you pay the same the entire time. And at the end of it, when you've paid everything off and they've made their money, now your power bill is reduced. But that's the game you play, is the reduction in cost. This gets more interesting once you add batteries to the equation. But for a long time, there were no batteries involved in solar just because the battery systems are too expensive.
So people could only use that energy in the daytime.
Right.
Once the sun set, you switch back to the power company.
Is using the power company. And you're probably almost always using the power company. There's only certain times of the day where it'd be purely solar. It just doesn't generate that evenly. And in places like California, where middle of the day there's a ton of solar generating, but it's also very hot, and so there's lots of air conditioning running. So there's actually pretty high power consumption in midday. Like
Right.
2 o'clock window is a high power area. Worked out just fine, right? That you're making enough solar to on your property to run your air conditioner, which tends to be power intensive, without actually pulling on the grid for doing it.
Hmm.
So,
It's cost effective, at least in the long run or medium
mhm.
term, and we've pretty much solved this idea of getting too much power back into the grid. Why isn't everyone doing it?
Well, we haven't completely solved those problems. Like we're still
Okay.
battling our way through them, and so in some ways we're comfortable with this early adopter model where the only 10, 15, some places 20% of people are doing this because the grid can cope with that. And
Hmm.
we're literally hitting walls where to go higher than that, we have to add more storage solutions, more transfer solutions. Things get more difficult. And so we've kind of, in some respects, we're starting to hit a wall in some areas about as far as you can go without making substantial changes. And storing electricity is difficult. It's not something designed to be stored.
Hmm.
Uh, we tend towards the battery solution because it's what we're used to. Like we have a lot of fancy batteries around us, whether they're in your phone or your laptop or
I
your
got a ton of them
car.
in my house.
Yeah, but when you talk about cost-effective power storage at grid scale, it's pumped hydro.
Hydro, okay.
So you pump water uphill to a reservoir. And then when you need the power, you let that water flow back downhill and spin a turbine with it.
Just like in
And
the old days.
yeah, well, it's not even that old days. It's, the reality is that hydroelectric power is a relatively rare resource because you need a combination of a water source at high altitude and a water receiving point, a river or something at low altitude. And there's only so many places where that's true.
Hmm,
But there's
okay.
a great study coming out of the University of Australia a few years ago that showed there's lots of places where there's water running available at the bottom of a hill and nothing at the top of the hill.
Hmm.
And so if you go up the top of that hill and dig a reservoir, put in the
And then,
pipe works like it's a dam, and when you
and
have
then pump it up.
excess energy, whether that be wind or solar, it's typically your sources of excess energy, you pump that water up.
Interesting. You live in Canada. I live in the United
Mhm.
States, and you travel all over the world.
Yeah,
And are there political implications to adopting alternative energy?
always. Because in the end, you're affecting people, and people live in groups, and those groups need policy, and so you have politics, right? I mean, all of these things are true. And for the problem is that the electrical industry has done such a good job of you not thinking about electricity that you don't think about electricity. You
I
expect it to
don't.
come out of the wall when you want to, right?
On.
It's just works, right?
Yep.
And in that sense, it's stopped being a precious resource. You just
Mm.
expect it to work. So most people don't know where their energy comes from and don't care. They've got other things to do. And so the idea of thinking in terms, all they want to do know is that it works. And so we
Mm.
ask our politicians to make sure they're experts that make sure that the power stays on, right? That's the thing we're motivated by. Now you're taking this larger factor of the impacts of power generation, and you have to have this sort of grown-up conversation. Says we should probably do it certain ways,
Right.
right? There are ways that cause less harm, that kill fewer people, that have fewer long-term consequences. Not that there any form of power generation has some consequences that are negative. It's just a question of what's the best mix. And so, we bring in experts to help us with, what's the most effective ways to generate power in our area. It turns out to be really regional too. A classic example of this, it doesn't add up to a huge amount of the overall power generation, but is everywhere in the world, is making power from biomass.
Biomass. What do you mean?
It's a generalized term for uh, leftover agricultural product. So when you thresh wheat, you have a leftover from that,
Okay.
right? And you need to do something with it. You can bury it in the ground, but then it decays into methane and has consequences. Or you can burn it and make electricity from it.
Hmm.
Now, it makes no sense to ship this stuff around. It's not the most efficient energy. But if you have an excess of this waste product that needs to go somewhere, turning it into power makes a lot of sense. So we have these small reactor solutions where they're able to burn at high efficiency, and it makes localized power, often for that wheat pool that's doing the wheat handling in the first place. And I bring that up not to say this is like the solution to everything. There is no solution to everything.
Hmm.
It's many little solutions working together. But we'll never have one. It's not going to be all solar. It's not going to be all wind. It's not going to be all nuclear. It's what's appropriate for the area that you're in. And
Interesting.
so, the reality is, and I've studied a lot of different areas of power generation, and every single area has 1 to 5% biomass power generation. And it's a pure reaction to they have a waste product that rather than do anything else with it, makes the most sense to make electricity from. If, we're super lucky in a place like British Columbia, much like Norway, we have a lot of mountains and we have a lot of rain. And so hydroelectric is easy here and power is quite inexpensive compared to the rest of the world. But that's just because of the geography that we have, right?
Totally makes sense. Maybe someplace like Kansas, which is very flat, but has a lot of agriculture.
Right.
Then,
so you're going to have a certain amount of biomass, but you're also going to have a fair bit of wind, right? Because as soon as you get up around 70, 80 meters, 100 meters up, some of those taller wind turbines, that wind's real steady and is a good power generation source. It depends on where you are as to what makes most sense.
I happen to live in a very windy city.
Yeah. And so, that has its advantages and it has consequences too, right? Like every wind turbine is its own power generator. So you need to synchronize a lot of different turbines, although we've gotten much better at that these days than we used to be. That used to, Denmark kind of led the world in wind power back in the 80s and 90s and solved a lot of hard problems that most people take advantage of. And it's why you see most wind generation companies come from, companies like Vista and the like, come from that northwestern part of Europe, because that's where a lot of the original development was done. That it's matured the technology to where we use it today.
Interesting. I know that we have, as a society, we've made some commitments to this. We were off camera, we were talking about the Paris Accords. Mm-hmm. I work for Microsoft, and we've made some commitments to, by a certain period of time, being carbon negative.
Right.
How are we doing on these commitments?
Well, all of these things are challenging, and there's a game to be played with how you measure them. Right. And there's a term called greenwashing for a reason. Often corporations read the room. They understand what their customers care about. And so they will make the noises that are appropriate for their customers. And at the same time, maybe try and do some good as well, because you're working at a certain scale. And when you're trying to do those right things, you're also trying to show progress. And so often there's situations where these are really difficult things to measure. For the most part, Microsoft doesn't make its own electricity. It has to buy it from various sources. Right. And these days, it's mostly about data centers. And they need more of them. So they're
massive data centers.
Yeah. And
take a lot of power.
These are tens of megawatts worth of power. And so, and their consumption tends to be 24/7. There's not a lot of variability once you get to this scale. And so most non-carbon emitting power sources like solar and wind aren't well suited for this problem, because they don't rise and fall with the wind or with with sunlight. And so they need more base load power. They need to be, or they're switching around from power sources. I mean, hydroelectric's excellent for this. And, you look at the Quincy facilities that Microsoft has in Eastern Washington, they're right beside a hydroelectric power plant. In fact, they're beside two. So they don't even need backup generators.
Right? They have in that location selection.
Yeah, there's a reason, and they got as close as possible to it, so they don't have to transmit the power very far. And those are inexpensive power, long lasting. I mean, it's also why you find typically aluminum refineries that are hugely power intensive close to hydroelectric dams if they can be, because it's inexpensive, large volumes of power that runs around the clock. Everywhere else, where you don't have that luxury, you need to generate power in different ways, whatever makes the most sense. Today, if you want to build a power plant quickly, and it needs to be base load, so it's going to run 24/7 as much as you need, it's combined cycle natural gas. Those power plants are relatively small. They're very efficient. They get the most power per ton of carbon produced, and they use natural gas, which is extremely inexpensive, because natural gas is a byproduct of extracting oil, for the most part, and it does not travel well. It can be piped, but it's hard. It's hard to store natural gas too. It doesn't like to be stored. You can liquefy it, but that's expensive, so it makes it, and then you have to deliquefy it to use it. So it's not a great product to transport. But if you have it locally or relatively locally, you can pipe it over thousands of kilometers if you want. It's a very cost-effective power source, and the combined cycle power plant is almost as efficient cost-wise. It's somewhere around the $40 per megawatt US dollar range, where wind is in the 25, 26, and solar right around that same point, $23, $24.
Another
So,
example of how there's different solutions for different areas.
yep.
It seems to be a local problem. But do you have a feel for how we're meeting the goals that we've set as either as governments or as companies? Are we on track? Are we ahead of
No,
schedule, behind
we're
schedule?
we're well behind.
Well behind.
Uh,
Okay.
the recent economic changes have been a part of this. Money got more expensive in the past few years with a little run of inflation and the raise in interest rates, and that
Mhm.
affects these large scale projects. Especially, when you talk about baseload plants like natural gas or nuclear, or even coal, you generally have to build the whole plant before anything works. And
Mhm.
so there's a huge upfront cost. You spend a tremendous amount of money before you start making electricity. And then over time, you earn out. It's one of the advantages of wind and solar farms is you don't have to build the whole thing. There's an initial setup cost to get the land configured and to get it connected to the grid. But if you've got 1,500 acres to build a solar, you can build the first 20 acres of it and get connected to the grid and get running and start a revenue stream and then add additional panels over time in blocks. Same for wind farms. They'll do an initial 10 or so turbines, get it up and running, connected to the grid and generating revenue. And then there maybe is 100 more they can add over time. So, one of the upsides to these new generation sources is that they're easier financially to develop over time and expand.
Hmm.
Where most baseload plants and hydroelectric being the most extreme version of this, where you have to do a lot of expense and construction before you generate the first water power.
One thing we haven't talked about is nuclear energy.
Mm.
And when I was a boy, that was being sold as the way of producing low cost, safe energy. And that perception changed completely about 40 years ago in Pennsylvania.
Well, yes, that
And
was one of the
now,
events.
yeah, and also in Ukraine as well.
Hmm.
But
Well, and there was the wind scale incident in the 50s in the UK, and then of course there
I
was.
don't. Well, I wasn't alive in the 50s, but I was alive in the 80s, and everything changed radically after 3 Mile Island and after Chernobyl, at least in perception. As far as I know, there are no nuclear plants even being built right now. There's still
There are.
some old
In
ones
fact,
running.
the
Oh, there are.
United
Okay,
States put two new nuclear power plants operational, the Vogtle plants in Georgia last year in
I
2024.
did not know that.
That was the first new reactors built in the U.S. in 40 years.
So maybe there is a future for
There's
nuclear
a
power.
resurgence in nuclear power. Now, I mean, 3 Mile Island was certainly part of the issue, but the bigger issue was nuclear proliferation. The movement against nuclear weapons had more to
Mm,
do with shutting down the reactors,
mm,
or the shutting down reactor development than anything else. The U.S. developed one of the reasons the light water reactor design won, which is the majority of nuclear reactors in the world today, 60, 70%. And especially if you combine both what they call pressurized water reactors and boiling water reactors. But either way, they're light water reactors. One of the reasons those reactors were matured is that a byproduct of operating the reactor was the production of plutonium. And so you build these fuel assemblies into large groups of rods, stack them together, and the spacing between them matters a lot. That sort of controls the rate of neutron interaction. And you're turning an enriched uranium stack, mostly uranium 238 and about 5% uranium 235. Run them for 6 months or so, then you shuffle them around again. And after about 2 years of doing that, many of those rods are damaged and you need to take them out. And then you reprocess them. The vast majority of the material in those rods is still uranium.
mm,
And so, but you will, out of a 50-ton rod assembly after 2 years, you'll have made about 200 pounds of plutonium, which is enough for a couple of dozen bombs. And so they
mm,
would extract the plutonium from that and it became part of the weapon systems. And so even in the 70s, um, when Carter was campaigning against Ford and Carter ultimately won, he campaigned on stopping nuclear proliferation. And in fact, one of the things that Ford responded to that by saying, hey, if you think that reprocessing fuel is part of the problem, then let's shut down fuel reprocessing. And in fact, they did. And the United States has never reprocessed fuel ever since. They just store their used fuel assemblies they have now for 50
mm.
years, which is a problem because they're mostly uranium. Like they're useful and they're hazardous. Like
Right.
but we found a lot more uranium. It used to be we thought uranium was precious, so reprocessing fuel was about getting that uranium back as well as getting the plutonium. But it is not. There's lots of uranium, and so it's easier to make new fuel assemblies than it is to reprocess old assemblies. So they've been leaving them alone. Not that the French do reprocess the fuel assemblies. The French also learned to reprocess fuel assemblies and incorporate plutonium back into their fuel, and burn that in the reactor as well.
Clever
So
people, those French.
yeah, well, the reality is that the reactor industry was funded largely by the military to produce
Interesting.
weapons, and so that movement in the late 70s, 80s to resist nuclear proliferation was a big driver on that. Uh, and it doesn't have to be that way. There are other reactor designs. The Canadians, who did not want to make weapons, went with a heavy water reactor design called the CANDU reactor that doesn't make near as much plutonium. But they developed those reactors in the 70s and 80s, and now 50 years on, those reactor designs are wearing out. They've just been run for a long time, and they haven't continued development of newer reactor designs. It fell out of favor, didn't get a lot of funding to continue to mature. But as we've come to appreciate the need for low carbon base load power, nuclear has got some real serious advantages. The problem is that the fear of it added a lot of regulation to it, to the point where it's extremely hard to build reactors.
I see.
And they build so few of them, nobody can get good at it. So the volatile reactor is a great example of this, because the AP 1000 plus design that they built down there, there's already 2 reactors that are an earlier design. They were built and delivered in the 80s. These new reactors have taken much longer to build than was expected, but they are what they call a passive shutdown design, or what called a Gen 3 plus design. They're actually simpler than the older reactors. When you're concerned about the safety of a reactor, you had a lot of sensors and a lot of fail safes and a lot of backups and so forth. But the big innovation that came in the later design of reactors now is that you can set up water flows inside of these reactors so that even if the pumps fail or any of these things go wrong, there's enough water and circulatory mass to let them cool down passively.
Hmm.
The Fukushima incident in 2011, which was a byproduct of the Sendai earthquake and ensuing tsunami, there are actually 6 reactors at Fukushima. We only ever talk about the 4, one of which was shut down. Number 3 was shut down, or number 4 was shut down, and 1, 2, and 3 had incidents because they didn't have a passive shutdown system. 5 and 6 had passive shutdown. Passive shutdown meaning if you lose power, everything stops, the reactor will just cool itself down on its own. But because 1 through 3 had these older reactor designs, they needed the pumps to continue running or the reactors would overheat. And those pumps, because they'd shut down all the reactors, needed to be run by diesel generators. And the diesel generators were in the basement of the buildings where they were told not to put them. They're supposed to put them on the roof. And then when the tsunami overtopped the tsunami wall, which nobody thought, it flooded the basements. And so they lost those generators. And so the reactors overheated, overpressurized, and emitted some radioactive debris and seriously damaged the reactors, breached primary containment, and now are a multi-decade cleanup problem. Passive shutdown reactors are just a better design. And so what's being built now, both in the U.S. with these 2 volatile reactors and in France and Finland and in England, are a different design, the EPGR design, which is also a passive shutdown reactor. The problem is that they've now, in the U.S., they've spent the money to build the first 2 prototypes at volatile. There's no plans to build additional ones. So the buildup of the skill set to make these reactors has been done, and now it's going to decay away. They're going to lose the skill set because they're not using it again, which is unfortunate. I mean, reactors get cheaper the more of them you build. And they're going to last 50 years. So in theory, if there was a campaign now to build more of this style of reactor in the U.S., they maybe need 20, and they could get them done over the next 10, 15 years. And then they would run for 50 years and you'd still have the problem, but presumably there'd be better designs after that.
Richard, we are just about at time here. Where are you speaking next?
I try and do as many conferences as I can, but and I usually get to do a geek out here and there. So I'll be at the NDC Melbourne conference down in Melbourne, Australia, and I'm doing the power generation talk this time for the state of Victoria, which is going to be fun for me to get up to speed on how
Melbourne's
Victoria
a great city.
It's a great city, yeah. And I'm going to spend a little time in Sydney, and I have family in New Zealand, so I'll go to New Zealand.
They're both great cities. All right, Richard, thank you so much. I appreciate your time. I learned a lot today.
You bet. I'll talk to you again. Like all energy generation is dangerous, but it can also be our friend. It makes our lives possible. But there's no form of energy generation that doesn't involve technology. Whether you're rubbing 2 sticks together or you're aligning very funny uranium-style rocks to boil water, it's all technology.